In this video, I'm going to discuss one of the questions from ISRO 2018 EC. The question goes as, for a network shown in the figure, calculate current I2. So for this network, we need to calculate this current in this branch, that is I2. So for solving this, I'll be using the most preferred, or I'll say the easiest way, that is I'll calculate this current I2 using Thevenin's equivalent. That is I2 is actually equal to VTH by RTH. So I'll open circuit this terminal by removing this 2 ohms resistance, and across this 2 ohms resistance I'll calculate the current I2. I'll calculate the Thevenin's voltage VTH and RTH, and then I'll calculate I2 as VTH upon RTH plus RL, where RL equals to this 2 ohms distance. So let's start. So to make this even more simpler, let's do some transformations. So let's convert this delta into star. We know if I'm doing delta to star conversion, and if all the resistances are similar, then in a star network, whatever is the resistance of delta network, we have to divide by 3, because all are equal value. Otherwise the formula goes as, if this is RA, then this value RA will be equal to 4 into 4 upon 4 plus 4 plus 4 plus 4 plus 4. That will be 16 by 12, that is 4 by 3. So this will be 4 by 3, this will be 4 by 3, this will be 4 by 3. So let's draw an equivalent network of this. So this is 4 volts, this is one resistance of 4 by 3, this is one resistance of 4 by 3, and this is resistance of 4 by 3. This is 1 ampere current source, and this complete part of the network. This is 4 by 3, this is 4 by 3, this is 4 by 3. Okay, and all these remaining part. Now what we can do, we can do the source transformation. Now this is a 4 volt in series with this 4 by 3 ohms resistance. So what we can do, we can convert this voltage source into current source by multiplying this with this, by dividing this by this, and the resistance 4 by 3 will come in parallel with this resistance. So the next step, this is just for simplicity what I'm doing. So this resistance will come in parallel with this resistance, 4 by 3 parallel with 4 by 3, and this 4 by 3, and here will be a current source of value 4 divided by 4 by 3, that will be 3 ampere, and then the respective. Before I'm applying the Thevenin's, before I'm applying the Thevenin's theorem, I'm doing the little bit of source transformation so that my circuit gets little bit simplified. Okay, so 4 by 3 and 4 by 3 in parallel, that will correspond to 4 by 6, that means 2 by 3. So these equivalent resistance of this terminal will be what, 2 by 3. And again, if you're converting this current source into voltage source, then what it will be, 3 and 2 by 3, 3 multiplied by 2 by 3, so there will be a voltage source. I think I can draw here. This is 2 by 3 resistance, so that 2 by 3 will come in series. This I can take as the voltage source, 3 multiplied by 2 by 3, this is a 2 volt voltage source, and in series with this is 2 by 3 plus 4 by 3, that is 6 by 3, and this is 2 by 3 and plus 4 by 3, 6 by 3, this is 3 ohms, this is 1 ampere, and then the remaining. this is 2 volts, and here. And if I'm further converting it, so this will actually become this 3 this is 2 by 3, and yeah, so this is 2 ohms only, not this is 2 ohms, not 3 ohms. 2 by 3 plus 3 by 6 by 3, this 2 ohms, and this is 2 volt. And again, if I'm further converting it, so this will become 1 ampere plus 1 ampere, so it will go as 2 by 2, so 2 in parallel with, so this will reduce to 1 ampere and this 1 ampere, so I can simply add these two current sources and make it as 2 ampere, this current source. And after transformation, only this portion will be what, it will be 1 ampere in parallel with 2 ohms, so that this 1 ampere and this 1 ampere I'm combining it, it is 2 ampere, and this is 2 ohms. And then the further resistance, this 2 ohms, this is 1 ohm, this is 1 ohm, this is 2 volt, and over here now let's apply by removing this resistance RL, I'm naming it as RL, I'm removing this, and then I'm applying here Thevenin's theorem, 1 ohm, 1 ohm, 1 ohm, and this is also 1 ohm. So let's start applying the Thevenin's theorem. So if you are seeing, if this I'm considering as A, terminal A, this is B, this is C, and this is D, can you see there is 1 ohm resistance, 1 ohm resistance, 1 ohm resistance, and 1 ohm resistance. That means this is a balanced bridge. Between D to A there is 1 ohm, A to C there is 1 ohm, D to B 1 ohm, and B to C there is 1 ohm. So if this is a balanced bridge, then across D to C there won't be current. So either we can consider this as open circuit or we can consider this as short circuit. Both way it works. Whatever you want to take, you can take it. So if I'm taking this portion and I'm considering that voltage in this source, voltage in this D to C is 0, and applying the KVL, it will simply go as minus plus I take the later portion of the convention. So applying KVL, it is 2 minus VTH, and what is the voltage? Voltage as C to D is equal to 0. That means VTH is actually equal to 2 volts. Or even if I'm taking from here, if I'm applying the current divider, then also I'll get the same thing. So that means VTH equal to 2 volts. VTH is nothing but the open circuit voltage. And now, considering this circuit only, calculate RTH. What is the condition for calculating the RTH? Since there is no independent source, so we need not to apply any voltage source from outside externally. For calculation of RTH, we have to eliminate all the dependent sources. Eliminate all independent sources, and eliminating independent sources means we have to open circuit the current source and short circuit the voltage source. While calculating RTH, we need to take care of only these things. If there is any independent source, we have to eliminate it, and if there is dependent source, then we need to apply externally a voltage source, and accordingly that voltage source upon the current through that voltage source will give the value of RTH. So here, if we are eliminating the current source, then what it will be, this 2 ampere will be suspended, only this 2 ohms, this, and voltage source, elimination of voltage source means short circuiting along it. This will be 1, this will be 1, this is 2, this is 1, and along this I need to find out the RTH. If I'm closely looking at and as usual naming this terminal, this is my terminal D, this is my terminal C, and what is this? This is my terminal. Yes, I removed this. This is my terminal A, and this is my terminal C, and this is my terminal B, and I need to calculate RTH across this. Now this we can actually make this is a delta connection. This is 1 ohm. Let's further simplify it. There will be one resistance over here, there will be one resistance over, and there will be one resistance over here. So redrawing the circuit it as this value of this resistance I can take over here, and this resistance I can take over here. This was the terminal D actually. This is C, this was what A, but now this was 1, this was 1. Now what will be the value of this resistance? Over here there will be a resistance. So this resistance will be 1 into 1 upon 4. So this is 1 by 4. This is 2 into, what is this? 2 into 1. It is between these two branches. So 2 into 1, 2 by 4. This is also 2 by 4, and this is 1. So these two resistances we can make out are in series. These two are in series, and we have to calculate RTH along this. So looking at this, whenever we are calculating RTH, we have to look from here, and that is how we can decide that which terminals, which resistances are in parallel and which resistances are in series. So equivalent circuit will be 2 by 4 plus 1 will be 6 by 4, that is 3 by 2. So over here the resistance of 3 by 2, this resistance is 1 by 4. Here is my RTH, and parallel to that will be 3 by 2. So this I can equivalently draw as this 3 by 2 and 3 by 2 are in parallel. So this will correspond to their parallel combination will correspond to, remember, if 1 by R is parallel, if R is parallel to R, then their equivalent combination will be R by 2. So 3 by 2 parallel 3 by 2 will be 3 by 4, and that from here there is RTH, and there is here it is one more resistance value 1 by 4. So we can say, from there we can say that RTH is actually equal to 3 by 4 plus 1 by 4, which is equal to 1 ohm, that is 4 by 4. And from here we apply the Thevenin's equivalent, and I2 will be calculated as, the equivalent circuit will be, this is VTH, this is RTH, this is RL, and the current through RL is I2. So I2 is nothing but VTH upon RTH plus RL. What is my VTH? My VTH is 2 volts. What is my RTH? My RTH is 1. And what is my RL? My RL equals to 2 ohms. This was a 2 ohm from where I started, because I open circuited this. So this is 1 upon 1 plus 2. So I2 equals to 2 by 3 ampere. So this is my answer. I2 equal to 2 by 3 ampere. So let's check with the options. Option A is the answer. I hope it's clear. Intentionally I did all these transformation to show you how we can make the circuit easier by source transformation, and we could have done it with different methods also by applying nodal and all, but I feel that Thevenin's equivalent, by applying Thevenin's theorem, this question has been much more simplified. Okay, thank you.